Hi Elvis, can I get a sound check?
Yes, you're good. Can you hear me? You are good.
Oh, Elvis, hi. Sorry, I had my microphone on mute. Thanks.
Yeah, you're good.
Okay, great. Thank you. So Elvis, were your parents music fans? Or it's a great name you got.
Thank you. Yeah, my mom definitely named me after Elvis Presley. She actually figured out she was pregnant in Vegas.
Oh,
Yeah. She also said she wanted me to grow up to be a very handsome individual. So
well, I can't see you, but I'm sure she got her wish.
thank you, thank you.
It's a great name. Are you an Elvis fan? Or
I don't listen to his music. I'm pretty young, so
yeah.
I actually have some questions about this class.
Okay, go ahead, Elvis.
So, have you watched who wrote the book for this class again?
It's a gentleman by the name, his last name is Razavi.
Yeah, he has lectures on YouTube. Do you recommend those? I don't know if you've seen them.
Yeah, highly. I really highly recommend him. I have seen him, and he's just a fantastic teacher, and great, great engineer, great scientist. He's really just an awesome, very impressive guy, and I think it would be great. So highly recommended. Yeah. He's actually at UCLA, as it turns out. So he's kind of local, I guess, in some extent.
Is he still teaching?
I think so. Yeah, he's not. Well, I guess compared to you guys, he's a young guy, but he's. Yeah, I'm pretty sure he's still teaching.
Hmm.
Oh, that didn't help. So Elvis, are you a sophomore this year, or what class? What year are you in?
Actually, a junior.
Oh,
Yeah,
junior.
yeah. So I'm taking my 33,000 series, and this is my only 2,000 class.
I see. I
Yeah,
see. So is there a 3200?
I don't think so, but I know there's a lab after this class.
Yeah. There's a 2200 lab, and I guess there's a 3200 lab also. But yeah, I'm not too familiar with all the different classes. Hi, good afternoon, Amy.
Good afternoon, Professor.
Hey, good afternoon, Aaron. Are you guys starting to have hybrid classes or in-person classes?
I think the ECE department is mainly online.
I see.
Yeah, all my
Yeah.
classes are online.
Hmm.
I have one kind of hybrid class.
And how does that work? Is it like every couple of weeks you get together, or?
Like every other Monday, it's in person.
I see. Yeah. It's funny. I always like one of the difficult things for me to teach in Cal Poly. I'm not like a full-time teacher there. Was to make the trek from Pasadena over to Pomona Tuesday, Thursday afternoons. And so that wasn't much fun. But yeah, I gotta admit, I kind of miss the in-person teaching. It's a little more interactive. But anywho, we'll have to make this thing work. All right, guys, I'll go ahead and get started. Let me just do a quick review. Sorry about this last Tuesday. I have some personal issues going on that I had to cancel, unfortunately, and I have a medical procedure, so I'm gonna put an announcement, but I also have to cancel for the in-person on Tuesday as well. So I'll for this coming Tuesday. So I'll go ahead and put up recordings for both of those and hopefully get us caught up in terms of the classes. But so anyway, let's do a review. So I think what we talked about in terms of microelectronics was that we are in this class and in, hopefully as you take more microelectronics classes in school or you see them at work, et cetera, once you graduate, we're going to be talking about this class of devices that are nonlinear. So an example of a linear device is something like a, let's say a resistor. And the thing that makes this resistor linear is if you look at the transfer curve of voltage versus current transfer curve for this thing. So this is the equation for the resistance, resistor, R is equal to V over I. So if you look at the graph for this, we basically have a type of function that is, if you sort of definition of a linear equation is if you're if you go in this positive direction versus negative direction, basically you get sort of a linear curve. And to some extent, capacitance the same way as if you look at capacitance has got something like this. And so if you look at the capacitance equation, let's see, if you do Q is equal to CV. So if I have charge here and voltage here, again, as I put more voltage across a capacitor, I get more charge and it's a linear equation. So if I put more charge on this side, I get a positive voltage. If I put more charge on this side, I get a negative voltage. That's kind of the definition of a linear equation. If you put in a negative, axis value, you'll get a negative version of the positive axis value. Okay, so I always thought, hey, linear sounds good, nonlinear sounds bad. But it turns out if you have some specific type of nonlinear behavior, you can use it for some really useful devices. For example, the first thing we're going to be talking about is this diode, which has, you guys are going to see this curve so many times. You're going to get sick of it, which is this voltage versus current, which has this nonlinear value. That means if you are, if you're here on this positive voltage, you're different. This negative voltage is going to look very different than the positive here. and we'll look at that. So it's in one direction or the other. And so this type of thing you can get from a material called a semiconductor. And so this is the basis of a lot of what we do in electronics. So using these nonlinear, not the diode necessarily, but transistors, which we'll see later. You can do, for example, binary math with this type of nonlinear devices, which if you guys aren't familiar with doing binary math, and it's basically, the basis of all digital functions we have. So it's like a very critical function that's in all our computers and cell phones. It sort of makes the world go around. And we can do, analog functions like gain is a good one, amplification. And we'll be talking about these in detail. But anyway, these are things you cannot do with linear devices. So you can do them with non-linear devices. So what's what these in the semiconductors, and these semiconductors are, they're sort of the ones we use, are interesting artifact of, if you look at the periodic table, the group 4 elements have this function. And this is a group that has silicon, it has germanium, and it has carbon. But we're mainly interested in silicon. And it turns out the reason it's called a semiconductor is that it's neither fully conductive nor fully non-conductive. So depending on some factors, it becomes conductive. So the first factor is if you had a pure silicon material, it would start getting conductive at some temperature, some temp greater than 0 degrees Kelvin. And there was a very complicated equation that described this for silicon. So I'll just put a proportionality constant, t to the 3/2, some exponential of minus e sub g over 2 kt. But basically, as the temperature goes up, you have this exponential and this to the 3/2 equation. So as the temperature goes up, the pure silicon gets more and more conductive, and it'll have more and more free electrons in the material. Another thing we talked about was that there are these free electrons that cause conduction in the pure semiconductor. And there's also something called the hole, which is the same as the absence of a free electron, which looks like it has a positive charge, and that also adds to the conduction. So I think I mentioned this in the last lecture we had, was that I would always be really confused about the concept of holes and thinking of them as are they like positrons or some new type of particle, or is it like antimatter? I don't know what the heck is this whole stuff. It's really just an artifact of being in a crystal lattice, and it's just simply the lack of an electron. So the fact that you have a lack of an electron, there is looks like a positive charge that's moving around, but it's literally this lack of an electron is moving around this gap, this bubble is sort of moving around in the semiconductor. So that's why it's called a hole, and it acts like as if it was a positively charged particle. And in a pure silicon material, the number of holes in pure silicon, number of holes is equal to the number of electrons. Okay, and each of them is equal to this in silicon. Okay, so then we said that by adding group 5 or group 3 type of elements into silicon, we can actually make the distribution of electrons and holes lopsided. So group 5 elements are things like phosphorus and arsenic. These are popular for this to do this with. And then group 3 elements are boron is kind of the main one we use. But you don't have to worry about the particulars of what those are. But so basically, what you do have to remember is that sort of these group 5 elements, these add an extra electron. So be above and beyond this number that you get at some temperature, for each phosphorus or arsenic atom you add in your silicon, you get an extra electron. And if you add instead, if you add group 3 elements, you get an added hole for each one you add. So be above and beyond what you get from this equation, you get an extra hole, okay, by adding group 3 elements. So either you can add electrons or add holes by this, and you do this in the factory. So engineers in the factory will make this device that has an excess of holes and an excess of electrons. And an important equation that we just asked, for us to ourselves to take on faith is this equation that the number of electrons and holes is always, this is always true, is equal to n sub I squared. So if you are in a pure silicon mode, n is equal to p, and so that, and they're both equal to ni, so n would be ni, p would be ni, so this would be ni squared. But this equation would also always hold, meaning that if you are in a piece of silicon or semiconductor where you've added some of this group 5 elements and you're getting an excess of electrons, so if you are making this artificially bigger than n sub I, means that you've had to make this artificially smaller. Okay, just happens that as you increase the number of electrons, you'll end up with fewer holes because this equation has to hold. So in a material that has this group 5 elements added, so this one is, when you add this material will be called just names, n-type. And the density of these, the group 5 elements is, they're called donors, and the density of donors is n sub d. So this is the density of donors. And that's in some number, I don't know, like 10 to the 12, 10 to the 15, whatever it is, they added per, so electrons per, actually it's more like atoms, I guess, per cube, it's always per cubic centimeters. And of course, the group 3 elements are called, when they are added to a piece of semiconductor or silicon, that piece of silicon will be called p-type. So n-type silicon will have a bunch of these donors, so-called, which are phosphorus or arsenic or group 5 elements added to it. And a p-type silicon has boron or a group 3 elements added to it. And that has, those boron atoms are now called acceptors. There's reasons for these names, but just have to kind of memorize the names. And that density is, again, the acceptor density. And that's n sub a again in atoms per cubic centimeter. Okay, so again, in that case, so if you have n-type silicon, so n ends up being roughly equal to n sub d. So P ends up being Ni squared over N sub D. And because this ends up, so by design ends up being higher than Ni, this becomes, would call this the majority. The electrons would be called the majority carriers in an N-type material, and the holes end up being called a minority carrier in an N-type material. And then in a P-type material, P-type silicon, where you've added group 3 elements, the majority carriers end up being P, and that's N sub A, and then, so this would be majority. And then the minority would be N's, which would be Ni squared over N sub A, would be minority carriers. Okay, I think that was that was all the stuff about, the densities, etc. Did you guys have any questions about that? That was like real fast forward description of what we talked about in the first lecture, but there's a couple of other items in terms of but at this point up to this, did you guys have any questions? Okay, so then let's see. So the other thing we said was, so now we have these extra carriers, or essentially these electrons and holes that are in the material, and they can lead to conduction. And there's two types of conduction that's possible in a silicon. So two types of conduction possible. One comes from having, if this is a piece of silicon, if you put a battery or a voltage source or something, basically a potential, across the silicon, you'll create an electric field. And because an electric field puts force on a charged particle, this electric field will give a preferential direction to charged particles. So if you had, this electric field, all the electrons, because they're negatively charged, would want to move in the opposite direction to the electric field. And all the holes that are positively charged, because they're positively charged, would want to move in the direction of the electric field. So basically, you're creating conduction in the direction of the electric field. Okay, so that's one type of conduction, and this is called drift. Okay, the other type of conduction is caused by the movement of electrons and holes. So if I, have, again, this is my silicon. So this is type 1, this is type 2. This is called diffusion. And so if I was gonna down here, this is X direction in the silicon, here is, say, the distribution of electrons. If I have a large number of electrons here and a small number of electrons here, the electrons tend to want to go from a place of high density to a place of low density. Okay, so, and this is, this isn't just because they're charged, but because that's all moving particles do, because of thermodynamic laws. you get a situation where, again, the good analogy was a drop of ink and a glass of water, or if you have gas in a container, the gas will uniformly just end up uniformly distribute itself in the container, or the ink will uniformly end up getting distributed in the glass of water eventually, because of this diffusion characteristic, where you'll continuously, stuff goes from higher density to lower density. But because there's this movement from high density to lower density, this creates essentially a current flowing, because there's movement of charge, that's sort of the definition of current. Okay, so I think that's where we ended last time, and there's the equations for the two types of currents, and we had in our slides and so on. So that's where we were at. Any questions about that? If not, then we can move to slide deck 2. And this is interesting, but I have no good explanation for it. This is just something that the drift current, and if you look at the drift current equation, these are current density equations. So current density is basically just current, you're trying to take out the area of the cross section. So you're just dividing the current by the cross sectional area of this stuff. So you just take out this cross section. So you get a current density. So you don't have to worry about physical size. So again, here, current density. But it turns out that the relationship in the drift current is this mobility mu sub n, and so the constant in the diffusion current is this d sub n, which is the diffusion coefficient. And these two end up, the ratio between these two end up being this kt over q, and k is Boltzmann's constant. This is just a physical constant. T is temperature, and Q is the charge of an electron. So, this is an equation which I know by heart, and but it's just sort of interesting fact that although these two components, these two current components are totally unrelated. I mean, they're both possible in a piece of semiconductor, but they're just two completely separate type of phenomenon. One of them is an electric field and charge moving, or the other one's from the difference in charge density, but somehow they're related. Anyhow, okay, so this is all, again, we're covering so much semiconductor physics. It's miles wide and miles deep, so we're covering a lot of ground here quickly, but this is the kind of stuff you just have to lay in the groundwork. So just giving you guys a background. Okay, so here, starting with stuff that we can do with this N and P material, etc. We can basically, this is sort of the basic function. So now we're talking about the devices we can create. With semiconductors. So we're going to talk about 3 devices in this class. One of them is diodes. One of them are diodes. I'm not even say that. It's good grammar there. So diodes, bipolar transistors, and MOS transistors. They're all nonlinear components. First thing we're going to talk about are diodes. the reason we're going to talk about diodes first is they're much simpler than these transistors, and it's like sort of an introduction to transistors in some ways. So I think this semester I'm going to try to go through diodes fairly fast. But, you know, again, depends on if you guys have a lot of questions, et cetera, about them. But they're the simplest of the three. And the reason they're the simplest is there's, you know, fewer stuff going on. These are, these two guys are 3-terminal devices. And that just means there's three connections, which means you have like 3 things interacting with each other. And diodes are 2-terminal devices. Meaning that there's only 2 things interacting, which is, you know, I guess a little simpler to deal with. So this is what a diode looks like. It's a piece of silicon where half of it they've put in, you know, an excess of group 5 elements. So let's say in this case, they've put in extra phosphorus on this side. Okay. So, and then, so they've made this N material over here. And then this is all happening in the factory. So they've put an excess of group 3 elements on this side. And so they're completely joined together. You know, it's not like we brought these 2 pieces separately together and glued them together or something. You just had this piece of silicon, and then you inserted phosphorus on this side and boron on this side. Okay, so that's sort of a block level, what it looks like in some sort of physics space. And this is what the representation in the schematic space. So we can design circuits with it. So this is the drawing for a diode. So I'll put it like that, but or whichever way you like. And this one is called, this node is called a cathode. So this is the N side. It's called the cathode. And the P side is called the anode. And this is something you're supposed to remember. I can never remember, but I always remember that this side is the N side and this side is the P side. So it's important to remember how this reacts when you're connected, but you know, I guess I just can't remember cathode and anode too easily, but I remember this is the N side and this is the P side. And of course it matters a lot because it's a nonlinear device. So you really have to keep track of it. And then there's 3, like I mentioned, if you look at a diode. So if I had a diode and I put a voltage across this guy, and let me actually draw it this way, so it'll be consistent. So let's say I had a diode, draw it like this. So again, this is the N side. This is the P side. So I guess this is called the cathode. This is called the anode. And then I put a voltage across this. As we'll see, what I'll get is this nonlinear voltage versus current function, where as this voltage goes more and more positive, past a certain point, for up to a certain point, there's no current. So it looks like an open circuit. And after I hit this sort of magic voltage, that is V sub 0, we'll see what this is. This guy looks like a completely closed switch. So it goes from something that conducts no current. Notice as my voltage is increasing, there's no current flowing. So this looks like an open switch, if that happens. And once I go past a magic voltage here, it looks like a closed switch, meaning that I get a huge amount of current flowing with very little voltage past that point. And then if I go negative here, then it just looks like a closed switch. And this is a non-linear function because going this way doesn't look at all like going that way in terms of the current versus voltage characteristics. So the best way to look at, if you're like trying to analyze, as we'll walk through why this is and how come this thing works like this, where it's easier to kind of look at three separate regions and how they work. So there is a region called equilibrium, which is, where the device is sitting. You're not applying any voltage. There's no current flowing. So kind of like around here. Okay. And then there's a region where you have what's called forward bias, which is over here. So this is called forward bias. This is kind of equilibrium. And this region here is called reverse bias. So we're going to look at each one of these regions and then put sort of why it acts like the way it does in each one of these regions. And then we're going to put an equation together. This, as you'll see, this is kind of a simplified drawing of really the current versus voltage characteristics. The actual characteristic looks kind of more like, it's more like this. So, and then we'll talk about the differences. But anyway, we're going to look at those three regions. So let's first look at the case of the equilibrium, where we're not going to apply any voltage. So here. Okay, so now if you have, oops. Okay, so we have a P. See if I want to draw it the same way as this so I don't confuse you guys. So we have N-type material here, P-type material here. Any questions, guys, by the way, so far? Just going quickly. Everybody following more or less? Okay, I'll count on you guys to stop me. But so, we have this N-type material here, P-type material here, meaning that if you remember what we said about the N-type material is that, so let me just say N-type material, so N-type silicon. So this is N-type silicon, and this is P-type silicon. So the N-type silicon has a bunch of extra donor atoms, and the P-type silicon has a bunch of acceptor atoms. So going back to our review a few minutes ago, we said that in the N-type material, the electrons are the majority carrier, and their concentration is about the concentration of the donors that we've injected in this. The donors are the N sub D is concentration of group 5 elements, like phosphorus. Okay, and the minority carriers in the N side, N-type side, minority carriers, or the holes, and their concentration is N sub I squared over N sub D. And if you run the numbers, so it ends up like this ends up being, maybe the number of electrons is maybe 100x the number of holes here, okay, on this side. It depends really on how many, the density of the donors that they put into the material, that ratio. But anyway, so that, so don't take the 100x is just, it's just a much higher, more, oops, much more electrons than holes. Yeah. go ahead.
On the left there, it says ND equals the concentration of what?
Group 5 elements. Sorry, I put in group 4, group 5 elements. Does that make sense?
Yeah, that makes sense.
And then N sub A here is concentration of group 3 elements. So here the majority carriers are P, and that's about equal to N sub A. And the minority carriers are the electrons, and those are Ni squared over N sub A. Okay, so if I was just gonna draw it in some funky way again, so if I, like, let's say overlaying, so this is an actual physical size. So now I'm going to overlay on this a graph of, so if I had, like, let's say I had overlay on this. So this is carrier density. Over here, I would have a lot of electrons compared to over here. So it'd be the number of electrons here are much higher than the number of electrons here, because the electrons are a majority carrier here, much higher than the number of holes. So if I was going to draw the density of holes on over here, again, I'm overlaying it, I would have this much holes here, and they don't have to be completely equal and opposite. So for example, this doesn't have to be exactly the same level as that. It could be lower or it could be higher than that. But the upshot is the electrons are the majority here and the minority here. So there's a big concentration of electrons here and a smaller concentration of electrons here, and a smaller concentration of holes on this side and a larger concentration of holes on this side. And in between, because this is sort of a continuous material, there has to be a continuous function that somehow gets you, whether it's a straight line or some kind of a other line, you have to somehow continuously get from here to here, depending, no matter what you do. So I'll just draw it something like this to be the same as the drawing that we have in our view graphs. And then same with the holes. Somehow in between, there's some, it goes from this low concentration on this side to higher concentration on that side. There has to be a continuous, because it's a continuous material. So somehow this might be happening very sharply, it might be happening very slowly, but basically you have to have a continuum between this side and that side. But the upshot, regardless, is that you have more electrons here than here, and you have more holes here than here. Okay, any questions about that? And so you end up with, this is a drawing, just sort of redrawing what I just drew. So a cleaner version. And to differentiate between the electron density on the n side, they call that n sub n. So that means electron density on the n side. That's that guy. And this is the electron density on the p side, so n sub p. So this is just to differentiate between this density over here compared to this density over here, and vice versa. So we have the hole density on this side, and on the p side is called p sub p, and the hole density on the n side is called p sub n. Okay, everybody good so far? Okay, so now we have this. Okay, fine. Now the first thing that, when you look at this here, is that we have a different in concentration. And when we described the type of motion of free carriers in a semiconductor, we described something called diffusion. Meaning if you're ever in a situation where you have higher density on one side of a carrier than on another, there's a tendency for those carriers to move from high concentration to low concentration to equalize the concentrations, okay? So what happens in this case, because you have a high concentration of electrons here and a lower concentration of electrons here, the electrons will try to move from here, this side to this side, makes this side, you're sort of dumping electrons from here to here. So this will try to go up in value from all the electrons that are coming from here. And this will tend to go down a little bit. Okay, and vice versa. The holes will try to go from here to here, just because there's fewer of them here. There's this tendency, because of this thermodynamic effect, because of this diffusion, for the holes to go from this side to that side. Okay. Any questions about that? Okay, so it seems like what would happen is you would start getting a current from one side to the other. And if you remember, I didn't go over it in the review, but in the previous lecture, we said that this current flow of electrons and holes, in the case of diffusion, it looks like it's kind of gonna be going not canceling each other, but it's going in inverse direction with each other. So they're gonna try to cancel each other out, or they're subtracting from each other. Cancel each other out is the wrong word. They're subtracting from each other, just because of one of them is, the electrons are negatively charged, the holes are positively charged. And so it looks like you get two different currents going in two different directions, and the total current is a subtraction of those two. Okay, so this is, again, we haven't connected anything to this thing. There's no external voltage. This is this piece of silicon the second after it's created, okay, or the millisecond or the microsecond after it's created. Is you don't have to connect anything to it. It's, comes to life as this thing that has higher density on this side of electrons than here, and vice versa on the holes. So it just comes to life like this, and then it tries to get into this equilibrium function where it's dumping these electrons to here and holes on from this side to this side. Okay, so I haven't applied any voltage, nothing. Okay, so at time 0, so this is a time step of what happens. At time to equal to 0, this guy has been given birth by the factory, and you've got, the N-type sitting next to the P-type material. The N-type's full of electrons. The P-type is full of holes. So that's the sort of the birth function. And immediately afterwards, what happens is electrons are going to pop from this side, where there's a lot of them, to the hole side, where there's few of them. And conversely, holes are going to try to go from this side, where there's a lot of them, to the N side, where there's less of them. Okay. So now what happens is, if you have electrons, remember that when you're looking at all these negative things here, these are they're being represented as free carriers, okay, that are moving around. But this chunk of silicon is still net neutral in charge, because each one of these carriers that got cooked off, either a silicon atom or a phosphorus atom or whatever, there is a positive charge in the nucleus of each one of these atoms. Now, those nucleuses are not moving. They are what's the word I'm looking for? They're stationary, okay? But if you add all the charge here, it's net neutral, okay? Because all the positive charges in the nucleuses has to equal the negative charges in the with the free carriers. So net, the carriers are all negative, but the net charge is neutral. Any questions about that? It's getting a little confusing, but. Okay, so here on the P side, similar deal, as you have the net number of stationary charge, the amount of stationary charge in the atomic nucleus is going to be the same as the net charge from the carriers, okay? But what happens is if you're getting electrons moving from here to here, each one that moves from here to here causes a net positive charge on this side. By the way, this thing is called a junction. So right where you go from N to P, that's called a junction. And this is called an N, so it's called an NP junction. Okay. So as you go from one side of this junction to the other, you end up getting a net positive charge on this side of the junction. And it happens to be, it's pretty local because, you know, initially these guys are moving physically from here first out, and then it goes, so you end up getting this positive, and these are stationary charges because these are these atoms that are in the material, and they're the nucleuses of the atom. So just sitting there. And it looks like a net positive charge now sitting here. And then vice versa on the P side, the hole's left. So it feels like you have a net negative charge, again, stationary sitting here on this edge of the junction, okay? And as time goes on, so this definition of T equals to infinity is, so this definition is equilibrium. Meaning the equilibrium means you've just, you know, you've put it in some mode. So the mode here is it's at a particular temperature and it's floating in space. So it's not, doesn't have any voltage across it. It's just sitting at a temperature. So at some point it'll get to quote unquote equilibrium where it doesn't, things don't change anymore. Okay. At that point, you've ended up moving some amounts of charges from this N side to the P side and the P side to the negative side. And you ended up with these stationary nucleuses that are positively and negatively charged on either side of this junction. Any questions about that? Okay, so now what happens as you get this positive and negative charges? So whenever you have a positive stationary charge and a negative stationary charge, you end up ending up with an electric field, okay? So as this event is happening with time, okay, so with time, you're putting, because of diffusion, you're putting, you know, you have a current flow because of diffusion with the electrons going this way and the holes going this way. And this is creating this charge, positive charge here, this negative charge here. So with time, you're starting to build an electric field that's getting bigger and bigger as you move more electrons here and you move more holes over on this side. So this diffusion current is creating an electric field. So diffusion current leads to an electric field across the junction, okay? And so we've got positive charges here, negative charges here. We start getting this electric field that goes from here to here. And interestingly, this electric field, whenever we have an electric field, we end up with drift current. So the drift current then leads to, the electric field, sorry, leads to drift current. Okay, those are, we said these are the two mechanisms. So mechanism one, mechanism two, these were the two mechanisms for current conduction in a semiconductor. So the diffusion came from the lopsided distribution of carriers on one side than the other. That led to movement of those charges and therefore an electric field. And then the electric field is now causing a drift current. And it ends up that that drift current is going in opposite direction to the diffusion current. So if you look at the electric field here from positive to negative, notice that because the electrons are negatively charged, they want to go the opposite direction of this electric field. So the other way to look at it is this electric field is opposing the movement of these electrons, the further movement of these electrons to this side. So because of diffusion, the electrons want to go to this side, but because of that, we built an electric field which is starting to oppose that movement. So this electric field and drift current at some point is going to stop the diffusion current. At some point, exactly at equilibrium, you're going to get this diffusion current. The more diffusion current you have, the more electric field you'll build up. And the more that electric field builds up, the higher drift current you'll get. And at some point, you'll exactly cancel the diffusion current with the drift current. And that's your equilibrium point. So without applying any electric field or anything, just this thing sitting at some particular temperature, you'll get this built-in electric field. An electric field, and it's basically stopping the current from flowing. So the net, what happens is you just get this built-in electric field even when you don't apply a voltage across this device. So and at this point, the drift and diffusion currents end up exactly canceling each other. Okay. Everybody, anybody have a question at this point? So like a sort of a negative feedback effect, I guess. I don't know how you want to look at it. So the upshot ends up being that, again, this electric field is minus the change in potential voltage or voltage respect to X. So there's a relationship when you have an electric field, you have a potential. So in devices, in semiconductor devices, or E&M, I guess, we mostly deal with electric fields and things like that and potential. But in circuit design, really usually don't think of electric fields. We're always thinking about voltages and currents. So instead of looking at this electric field, we actually look at this as a voltage or this built-in potential or built-in voltage, which comes from the built-in E field. Okay, and then, I'm not gonna derive this, but it ends up that this electric field gives you a voltage with this equation. So these are the important equations here in the end. And basically the way you solve these equations is you make the drift and the diffusion currents equal to each other, and you go through and integrate and so on, and you end up with this built-in, so-called built-in potential V sub 0. Okay, so this is, again, this is what happens when, so if we said we had a diode. And so we have a diode, and we have a, so I happened to be in San Diego today, giving a lecture at my brother's house, and he just walked in. I don't know if I remember our first lecture, that he's also an electrical engineer. So this lecture is probably making his hairs rise on end. Anyway, sorry. Anyhow, but let's see, where was I? So if you draw this diode, we end up with, this function I said. So this is this V0 here. This is the equilibrium point. We don't really apply any external voltage. It's just sitting there, and it's, you're completely, or actually, I'm sorry, it's just sitting at V0 here. So if I have this being the external voltage, sorry, let me redraw this. Got distracted by my bro. Okay, so again, if I draw voltage versus current here, the equilibrium point is really here. Okay, where we're not, the external voltage is 0. I'm not applying any external voltage, but because the currents are canceling each other out, I have 0 current. So this is the equilibrium point. There's no current even at, when I don't have any external voltage applied. Okay, and that built-in potential is this guy. Okay, any questions about that? Okay, so that's the equilibrium point with this built-in potential. So when you do not have any external voltage applied, you have this potential inside this junction that's perfectly canceling the two currents without any external voltage applied. And this sort of creates, to do that, you sort of have this built-in potential, and this is the equation for it. So one thing about the equation is that, you can see it's dependent on this KT over Q. You'll see this KT over Q a lot in this class. Okay, so again, K is the Boltzmann constant, T is the temperature, Q is the charge of an electron. So the Boltzmann constant K and Q, the charge of an electron, are just one of those physical constants from physics. They're just numbers. I wish I could give you some insight about why the charge of an electron is 1.6 times 10 to the minus 19, or the Boltzmann constant is whatever it is. But, I guess I don't really have any insights about that. They're just constant. And then if you are at a particular temperature, right? If your temperature is constant, this KT over Q component is a constant. So regardless of what they do at the factory or whatever, you take that PN junction or that diode, this ends up being a constant, and you know what it is in the lab or in your cell phone or whatever, you know what that number is. Now this part, which is sitting in the natural log equation, okay, this now is dependent on what they did at the factory. So this is the acceptor concentration on the P side. This N sub D is a donor concentration on the N side, and I squared is just, that's also a constant as a function of temperature and the material you have. But basically you end up with this equation for this built-in potential. Okay, so that's the equilibrium point. Then you can then we can look at a couple of other regions, which is when you have, so this was the case, the equilibrium point is when, so this is when let's call this V sub D. And V sub D is equal to 0. Okay. And let's call this again V sub D. We got our diode. So let's look at the case where V sub D is negative. Sorry, is positive in this case. No, it's negative. Sorry. Is negative. Okay, so remember, this is the N side. And this is the P side. Okay. So I have more voltage. Okay. There's a higher voltage on the N side. So if this is negative, V sub D is negative. So again, this voltage current, as if I'm operating here somewhere, I have more voltage on the N side than on the P side. Okay, so I've put a higher voltage on this side than this side. And this region is called a reverse bias. It's just, these are just names that they gave to them. So anywhere over here, you are in so-called reverse bias. Okay, so remember that the electric field, in the case of no voltage, the electric field was pointing this way. Okay, so this top guy is no voltage added. So the electric field was pointing that way. And the electric field is minus dV dx. So if we looked at the built-in potential, because of this negative sign, the built-in potential is sort of looking like this. It looks like there's got a potential from, so the electric field is going this way. It looks like the built-in potential is going that way. So when we're in this reverse bias, and when we're in this part of the graph, it looks like we are enhancing or adding to this built-in potential. So we're even resisting the flow of current even more. So just because of the way we're just going in the same direction as the built-in potential. So we're putting more and more positive ions on this N side than the negative side, and this is opposing the diffusion current even more. Okay, now, like, in some sense, like, what does it mean to oppose the diffusion current even more than it being 0, right? It just stays 0. So when you're over here in reverse bias, the diffusion current ends up being still 0. So it started at 0 here at the equilibrium point, still is 0. Okay. But one thing that happens is, as you get this region, so this is a physical region that's growing in size. Okay. So as you apply this reverse bias more and more, as you put more and more, if this guy, we can think of this as being more and more negative compared to this point, or this point being more and more positive with respect to that one. You can think of it as either way. You get more and more of these built-in charges here across. And so one way to look at this is, this looks like a capacitor where the two plates are growing further and further apart. So the plates of this capacitor is where you have conduction on either side, and these are moving further and further aside. There's no conduction. So here, inside here, there's still electrons, free electrons, and inside this part, there's still free holes. But in this middle, this thing is called so-called depletion region. So depletion region. Meaning it's depleted of carriers. So there's no conduction happening inside here. And it just looks like you've got a capacitor because you've got, like, this is again one plate, this is the other plate of the capacitor, and this is non-conducting, this is non-conducting. Looks like they're moving further apart. So although when you go to more and more negative voltages, there's no change in current, the capacitance of this device, of this diode, is increasing. Okay, so so basically if you look at the capacitance, if this is the reverse bias, as the reverse bias increases, or sorry, as the reverse bias goes closer to zero, as it decreases, you get a higher capacitance, right? As these plates get closer to each other, the capacitance goes up. As the plates move further apart, the capacitance goes down. So with the reverse bias, you end up in this variation in capacitance, which just turns out to be square law dependent on the voltage. Okay. So you can use this diode now for if you wanted to build in or create a voltage dependent capacitance. And one favorite place for this is like an oscillator. So I don't know if you guys remember, maybe hopefully you guys saw this in your previous classes, is if you have a LC circuit. So if you put a capacitance in parallel with a inductor, you end up at some frequency, you end up having an oscillation here, as the inductor is putting sort of charges get put on the capacitor, and at some point the charges go back through the capacitor through the inductor, and etc. So it's just moving charge from one side to the other, and this thing is oscillating. Now by putting in a reverse bias across this capacitor, you can actually, because we're changing this capacitance, we're moving the resonant frequency of this oscillator. So this is one particular circuit you could use it for. For example, if you have, let's say, if you wanted to have a particular carrier frequency in your cell phone that's like, maybe it's 2.4 gigahertz or something like that, you can tune it pretty precisely by changing this voltage to get to a particular frequency. So this is an example of what you could use this reverse bias diode for. Okay, so that's the reverse bias direction. So now we've covered, again, in a diode, we've covered sort of this region. So we've covered this region where we have no voltage applied and where we've got negative voltage applied. So then now let's look at what happens when we go in this direction. So this direction is called forward bias. Okay, so this is the case when I am putting more positive voltage here on the P side. So I'm putting more positive voltage on the P side than the N side. So applied this. So I'm putting more positive voltage on this than this. So again, if I look at V sub D versus I, I'm over here. Okay. So notice now, again, the built-in potential was like this. So now by putting my battery or voltage source, I'm putting it in the opposite direction as the built-in potential. So I'm reducing that built-in potential with this external voltage. The built-in potential was just enough to stop the current, the diffusion current from flowing. So as I reduce it, I start getting a current now. Okay, as I'm reducing that built-in potential, I start getting a diffusion current again. So that's kind of what's happening here. As I am, so there was, without any external voltage, I just had enough electric field here to stop the current from flowing from the diffusion current. But as I reduce that, I artificially reduce that voltage, I start getting more and more diffusion current flowing. So I ended up with this equation. So this is just another way of, so we didn't really solve this equation, but this was sort of in a piece of P, piece of N in a natural log function. So this is, you can rewrite this as an exponential function if you put it in terms of piece of P and piece of N, which is what this is doing. So it's really the same equation, but in the form of an exponential instead of a natural log, by if you want to figure out piece of N and piece of P. And it ends up, you can basically look at the voltage, the forward bias voltage is reducing from the built-in potential. Okay, as you are increasing this forward bias voltage, you're increasing the diffusion current. And you're increasing the diffusion current very quickly because it's in an exponential function. Okay, so once you're in this forward bias direction of voltage, a little bit of forward bias, so a little bit of added voltage because of this exponential function is going to give you a lot of extra current. Okay, so let's see. Let's say here. So if we put all this together, so this is all in all, this is the, so I drew the thing. So again, this is my diode. Let's say this is the current going through, this is I sub D. And there's my simplified drawing was that I had sort of this region where I was, reverse bias here. And forward bias here. Okay, so this is sort of a simplified drawing, but because it's not quite this abrupt, so this is like a real simplified type equation. The real equation looks like this, the real graph of how this thing works. Real life is always, I guess it's a little smoother. So if I actually look at the current, it ends up being something like this. As opposed to that. Okay, so this side looks like, so here I sub D is kind of proportional to an exponential function of V sub D. Okay, we'll fill this out, but here with increase in current V sub D, I get a real fast drop. I mean, it's the way to show it is, hopefully I'll do it next time if I remember, is doing it in Excel, you'll see how fast this current takes off. It really looks, and I'll keep drawing it like this, but it really looks a lot closer to that, like really sharp exponential takeoff in current as you go forward bias. And as you go to reverse bias, you end up having a small current. It should be really like zero, but this is a very, very small current. There's always some current, but this is a very, very small current. But there is a current nevertheless. Okay, it's not quite zero. I can give you the reasons why it's not quite zero. But it's important. It's unimportant for us at the moment. But there is a current, but it's very, very small. Okay, and overall, the equation. This is where I'll stop today. Is the total I sub D equation for this full curve. So for this full curve, ends up being I sub S Okay, so this is this I sub S. Okay, so this is a small number typically. So it's like 1 times 10 to the minus 15 amps or something like that. Well, it's a function of a lot of things. It's a function of the junction area, the charge of an electron, the diffusion constants, the donor, it's acceptor and donor concentrations, etc. But you can think of it if you get a diode from the factory, this is a constant for each manufactured diode. So once the factory's built this diode, this I sub S is a constant. So if you look at a data sheet that you get when you buy the diode, this I sub S is just given to you as a number, okay? So that's this I sub S times exponential of times V sub D over V sub T minus 1. And this V sub T is defined as KT over Q. Okay, so this is the full equation for this diode. So what does this look like? As V sub D gets negative, so this V sub T is a number, like I mentioned, this is just shorthand for KT over Q. Remember, this was this, where do we have KT over Q? Remember, it was the part of the built-in potential, but it's really a constant at a particular temperature. So this guy, so at, say, at 300 degrees Kelvin, V sub T is around 25 millivolts. Okay, so what happens? As V sub D gets negative, so out here, so as this thing gets negative, this quickly, because it's an exponential function of a negative value, it ends up, this guy quickly goes to 0, and you end up with, ends up being 0 minus 1 times I sub S. So end up getting minus I sub S here very quickly. Okay, and as you're positive, so as V sub D gets positive, again, it's an exponential function. So as V sub D gets positive, you very quickly, this becomes much bigger than minus 1. And this side of the equation ends up being, I sub D ends up being approximately, or sorry, proportional to approximately exponential of V sub D over V sub T. Okay, and that's, and exactly at 0 V sub D. So if this was exactly 0, this ends up being 1, and then this is 1. So you end up with 1 minus 1, and you exactly end up with 0 current at 0 voltage. Okay, guys, I'm going to stop here. Any questions?
Yeah, for like the last part, when you said I sub D is approximately IS exponent VD over VT, that becomes like that when V of D is very high.
That's correct. And it doesn't have to be very high. It just has to be higher than this 25 millivolts. So this is this ratio V sub D with V sub T, and V sub T is a pretty small number. So, you know, like if V sub D is 250 millivolts, this is already 10. Because it's, you know, it's 250 millivolts over 25 millivolts. So even when you have a few hundred millivolts, this ends up being a very, very large number.
At that point, the -1 is kind of just neglected.
Exactly, yeah. So this is like a sharp takeoff and very close to this point, as we'll see, very close to the zero voltage. This typically, anyway, I'll give you typical numbers.
Thank you.
Sure. Any other questions? Okay, guys, thanks. Have a good weekend, and I'll see you guys again Tuesday. I'll put this up in the announcement again. I have to unfortunately cancel the live class on Tuesday. So I'll see you guys next Thursday. Take care. Bye.
Thanks, Professor.
Oh,
Thank you,
Professor.
Yeah.
I was wondering if you're going to upload today's session and then last week's session as well, like the
Yeah.
recording.
Yeah, I'm sorry I didn't do that. I'll do that tomorrow.
Okay, no worries. Thank you so much.
Yeah, thank you.
All right, thank you.
Bye.
Thank you, Professor. Have a good Labor Day weekend.
Thanks. You too. Take care. Bye.
Thank you.